All right, lecture 65, confidence intervals, facts, and issues. I just want to clean up a few things here. We're not going to do any more confidence intervals for any more parameters. I think we've done enough, but I want to just say a few things here. So first thing, point estimate and margin of error from the confidence interval. We've seen that the confidence interval for means, difference of means, and proportions are symmetric about the point estimate. We get a point estimate and a margin of error, go down and up. So the point estimate lies right in the middle. All right, so this means, that given just the confidence interval for one of these parameters, you can find both the point estimate and the margin of error. Example, suppose we're told that a 90% confidence interval for the proportion of students who approve of Drury's cafeteria food is 0.12 and 0.20. So the confidence interval is 0.12 and 0.20. And I say, find both the point estimate p hat for the true population parameter p and the margin of error e. These are very easy. Here is 0.12, and over here is 0.20. Here is p hat. It's right in the middle. What's right in the middle of 0.12 and 0.20? The average, correct? If I want the point right in the middle of those two, I'm going to take their average. So p hat is 0.12 left endpoint plus right endpoint divided by 2, and that's, of course, 0.16. So p hat is 0.16. All right, what's the margin of error? The answer is, give me the right endpoint and subtract off p hat, and I get 0.04. So that's 0.04. That's my margin of error. And likewise, I could have just done it like this, 0.16 minus the left endpoint. The point estimate minus the left endpoint would also give me 0.04. It better give me the same answer. If not, I've made an error somewhere. So that's easy, isn't it? Next example, suppose we're in a 99% confidence interval, or we have it, of the weights of men and women in pounds, the difference of the weights, let me read it again. Suppose a 99% confidence interval for the difference of the means of weights of men and weights of women in pounds is 27:49. So the confidence interval is 27:49. What is the point estimate, which is going to be like x1 bar minus x2 bar for a difference of means, right? This is the point estimate. It has to be halfway between there, 27 plus 49 over 2, which is what? 38. What is E? I just take 49 minus 38, or 38 minus 27. 49 minus 38, and I get 11. All right. So this is if someone has already done all the work and they're just giving you the confidence interval, and you'd like to know, well, what point estimate did you come up with? Here's how you get it. What margin of error did you come up with? Here's how you get it. You don't have the original data to do the calculations like we've been doing. You just have the confidence interval. That's all you need. Okay. And I point out here, note we cannot use this method to find the point estimate for a standard deviation or variance given just the confidence interval. The reason is that the confidence interval is not symmetric about the point estimate. The point estimate is going to be inside the confidence interval. It's going to be shifted. So I can't take the average of the two endpoints and give me the point estimate. That's not going to be the correct point estimate. So it doesn't work for a variance or a standard deviation. On to the next page. Confidence interval size versus confidence level. We've seen that the higher we want to have our confidence that our interval contains our desired parameter, the larger we have to make the interval. All right. So to get a very high level of confidence, we may have to make our interval so wide as to be kind of ridiculous. Like I think I said before, I can always tell you that, hey, minus infinity to infinity is 100% confidence level, confidence interval. But that's a very stupid interval. It doesn't tell you anything about where the parameter is. It's somewhere between negative infinity and infinity, which is a ridiculous thing. But I got 100% confidence. That's kind of crazy. If I want to get a high level of confidence, I may need to have a very, very wide interval, so wide that I don't feel like I'm really giving you much of a good ballpark estimate. But we've also seen we can decrease the size of the interval at the same confidence level by increasing our sample size. That shrinks down that margin of error. This is the trade-off, to have both a small interval and a high level of confidence that the interval has captured the true value of the parameter. So if I want to zero in real close and be highly confident that inside that tiny interval I have what I want, it's going to take a big sample size. Look at this example. Suppose we want to estimate the mean weight of adult wombats in kilograms. We take a random sample of size 25, assuming it's normal, or yeah, we don't even need that here, but yeah, well, it's less than 30, so we're going to assume it's normal. We compute the sample mean to be 28.2, sample standard deviation to be S is 12.3 kilograms. 99% confidence interval turns out to be, 28, let's see, I say it's 28.2 plus or minus E, where E is T, you should work this out very, very fast, S over the square root of N. That's how we do for a mean, right? And that works out to be 6.88. 6.88, maybe exactly 6.88, I think. So it's, so 99% confidence interval is 28.2 plus or minus, we'll round up to 6 to the nearest 10th, 6.9. Okay, and that's good to round up because now each one is a little bit past. So I definitely have 99% confidence interval. Okay, but I'm like, it's within 6.9 pounds, or sorry, kilograms. That's, maybe kind of a little wide for what I want. I still would like a 99% confidence level, but I want to narrow that. Can I keep that high level of confidence and narrow it? And the answer is yes, if I increase the sample size. So I say, suppose we want a smaller margin of error, thus shrinking the interval. And suppose we want to more or less halve the margin of error. All right, suppose I want to halve this down to, it's almost 7 now, so halve it, get it down to like 3.5. So I got my answer within 3.5 kilograms instead of within almost 7 kilograms, one way or the other. How do I do that? The answer is increase N. In fact, let me say it right here. Here's the margin of error. I'm dividing by square root of N. If I want to divide by twice as much to make it half, under the square root, I have to make N 4 times as big, because when I square root that 4, it'll be 2. So I basically want to quadruple N. All right, so however many I used 25, and I got this. I'm going to have to go out and get 100 of them, a lot more work, right, to get a narrower confidence interval that's still 99%. That's maybe about half. But here's the thing. If I do that, I'm not guaranteeing that I'll cut the interval in half. The reason is because it's a new sample. What do I say here? I say, yeah, but this is a new sample. So I have to recalculate S. So S might be different. If S is different, then, this it might be, this number will stay the same because that's gotten from 99% confidence. Actually, no, it changes too, doesn't it? Because my degrees of freedom are different. They were 25 minus 1, now they're 100 minus 1. So that number changes, and that number probably changes as well. So we've changed things a little. So even though we're dividing by 2, the fact that we changed it means we might not get exactly half. It might be a little more than half, it might be a little less. Okay, but you can kind of see, assuming these don't change a whole lot when we recalculate everything, by quadrupling N, going out and getting 100 wombats instead of 25 is a way I can cut the confidence interval probably pretty close to in half. All right, so that's the kind of thing you have to do. That's a trade-off. You can get high confidence in a small interval, which is very, very good, but the cost is that you have to get a much larger sample to get any appreciable shrinkage of your confidence interval. And you could even get a higher level of confidence. If you go out and get an even bigger sample, you could keep the confidence level, keep the confidence interval at, half of what it was and get an even higher level of confidence if for some reason you would need that. But we'll stop there with that. I just want you to be aware of the trade-off there. Finally, confidence intervals compared with hypothesis tests. And I say you've noticed that there's a strong connection between confidence intervals and hypothesis tests. In both cases, Critical values are used either to mark the boundary between usual and unusual values in a hypothesis test, or to help construct the margin of error for a confidence interval. When we've had to do that, which not in the case of variance or standard deviation. But anyway, the following sentence is not always true, but it can help you understand the connection a little better. Any value that lies outside a 101 minus alpha % confidence interval will have a test statistic that lies in the rejection region at the alpha significance level for a two-tailed hypothesis test. And any value that lies inside the confidence interval will have a test statistic that lies inside the non-rejection region. What does that mean? Well, let's do a little example here. I say that the statement is true for means, difference of means, and for standard deviations and variances. It isn't exactly true for proportions because the calculations for confidence interval building and hypothesis testing for proportions use slightly different numbers. If you go back and look, for hypothesis testing, we used pooled proportions. We didn't do that here. So things are slightly different. So it doesn't quite work there, but it works for the other cases. So for example, suppose you compute a 95% confident interval for the mean lengths of adult wombats in centimeters to be 94.7, 103.9. So this is the 90. Let me see if I got something here that won't squeak. What will this do? Well, it's going to squeak, but at least it shows up well. 95% confidence interval is 94.7, 103.9. Suppose you've computed that. Incidentally, you can go through and find the point estimate and the margin of error, but I'm not going to do that. Instead, I'm going to say, then you could reject, since this is a 95% confidence interval, 101 minus alpha % is 90%, alpha must be 0.05 or 5%. So you can reject at the 5% significance level the statement that the mean weight of a wombat is any value outside this interval, say 105 centimeters to the right or 93, which is to the left. But you would fail to reject the statement that the mean weight is any value inside the interval. So in other words, if you had this, if you were looking at a hypothesis test where H naught was that the, let's see, lengths of adult wombats, all right, for some reason I have a difference of means here. I have to fix that before I give that to you. All right, so that mu is, let's say, 105, and that H1 is that mu is not 105, okay? What we have done then is our confidence, our 95% confidence interval is right here, and since 105 is outside that, we reject H naught at 95%, at 5% significance. At alpha equal 5% significance level, all right? What if it were, that one I guess is already in there, we reject H naught at the 5% significance level. The next one is, what if mu, the null was that mu equals, 93, I say, and this is the one you have to fill in, and the alternative hypothesis is that mu is not 93. 93 is not in this interval, it's over to the left. So we reject H naught at alpha equal 5% significance level. Lastly, one more to fill in. H naught is that mu is equal to, what do I say, 98. And so the alternative hypothesis is that it's not 98. This time, since 98 lies inside the 95% confidence interval, we failed to reject H naught at alpha equal 5% significance. Significance level. All right? Yes. All right, so this is why I kind of like, generally I like confidence intervals more than hypothesis testing, because you actually get a value that you believe is your best guess as to what the parameter is, and then you have an interval that gives you this level of confidence, however high, that you're sure the parameter is inside, you feel it's inside, and also you can use it to do hypothesis testing, right, because using this equivalence here. All right, so I really like confidence intervals, and so I'm glad we have done them. So we're going to stop here with that.